Boom. Make sure I got my stuff going. Very good. All right. So we had worked on our section 4.3. It's kind of a long section, right? Dealing with the first derivative and second derivative discussions of how it informs us about the graph of our function, right? Those intervals of increase and decrease. For the first derivative, our intervals of concavity. I know we only went like 1 or 2 examples there, but hopefully with what we had done with the first derivative, that work starts to kind of come together. That concavity discussion we'll start to discuss more thoroughly, definitely as we start to get into our more formal curve sketching in the next section, right? But trying to get through some of the calculation work and whatnot first, let's start to look at our dot cam. All right, so there we go. So we should see the dot cam. I'm recording. Very good. So we're going to kind of wrap together in section 4.5 the work that we've been dealing with in 4.3, right? Looking for those absolute maximum minimums in 4.1. The mean value theorem truly doesn't come up too greatly in our graphing application, right? So now let's look at one more aspect, a question that was brought up as we were looking at those intervals of increase and decrease, right? What's happening at the ends of our graphs? How do we know what's happening out there? Are we going to have an absolute max later, okay? Or is the first derivative test that we do with our critical numbers giving us an absolute max or just a local max, local min, whatever it might be, right? So we're kind of getting into that discussion. All right, so with that said, let me get my windows to match up. There we go. So let's look at section 4.4, and we're looking at indeterminate forms. Forms, plural, and LHopitals rule. Okay, this, I believe, French mathematician, L'Hopital. Okay, we'll talk about that. But when we're looking at these indeterminate forms, really what we're going to kind of focus on is this kind of end behavior for our graphs. Looking at those limits as x goes to positive or negative infinity for our function, okay? And we're going to kind of start to inspect, are we going to continue to climb to infinity, fall to negative infinity, right, continue to decrease, or possibly at the ends, are we going to have a horizontal asymptote, right? So that way, if we do have a horizontal asymptote where we flatten out, when we start talking about for those maximum minimums, we can identify, okay, that is going to be an absolute max because our function kind of levels off at y equals 1 everywhere else or whatnot. And we can start to see those as absolute maximums. If our graph continues to climb without bound, drawing to our infinity, negative infinity, right? Then we know there's not going to be an absolute max or min, okay? But it'll continue to grow, as I said, without bound. It'll continue to get more and more positive, more and more negative, dropping down like our parabolas and so on, that kind of quick common graph, all right? But we're looking at these types of limits, right? So let's take a second here. Let's recall, let's think back, okay? Back in chapter 2, I forget what section, it might have been section 2.6, possibly, I think, those limits involving infinity, okay? But remember we had taken, for example, a problem where we had this limit as x goes to infinity of our rational expression, most common, right? We had those shortcuts we would do in pre-calculus. We learned a more formal kind of calculus version of this. If I like 4x cubed minus 5x squared plus 8x minus 9 over, in this case, let's say 6x cubed plus 2x squared minus 4x plus 1 is making up this function, okay? And we want to take that limit as x goes to infinity, or we can do negative infinity. We had some problems involving radicals, which kind of took some interesting algebra, right? But before, I know we have the shortcut from pre-calculus that if we have a rational function where the numerator and denominator have the same degree, the same highest exponent on that variable in the polynomials involved. We could just take the ratio of our leading coefficients and use that for our horizontal asymptote, right? It's really kind of narrowing in on those results. That was our pre-calculus discussion, and what allows us to do that, what allows us to take that shortcut and that quick calculation is because we would take that problem, recall, and we would divide everything, all those terms, by the highest power of x we had, and in some discussion we would say in the denominator, the highest power that appeared, okay, in case there was different degrees for numerator, denominator, or we can just do from the entire expression the highest exponent, the highest degree we had on our variable, right? And I know, again, I'm kind of running through these steps, but what we did back in chapter 2, I asked you guys to divide by the highest power of x, right? Simplify down. Where we end up with 4 minus 5 over x plus 8 over x squared minus 9 over x cubed in the numerator, 6 plus 2 over x minus 4 over x squared plus 1 over x cubed in denominator, pushing that up, okay? So hopefully it's starting to jog your memory, okay? And then by taking a limit as x goes to infinity, right, gets really large, bigger and bigger, all these rational expressions, all these fractions with variable left in denominator, is going to be 5 over some really huge number, that these terms with x left in denominator are all going to go to 0. Those get smaller and smaller. They become ineffective in our discussion. And so in the end, that limit comes down to 4, 6, right? The ratio of our leading coefficients. And of course, we simplify to 2/3, right? And so we would get that value for our limit. I'm going to zoom out a little bit. We get that value for our limit. And we'd say that, okay, for that function, we would have a horizontal asymptote at y equals 2/3, right? That as we extend that graph out, plotting more and more points, as x got really large, the y value would get closer and closer to 2/3. Okay? So giving us that aspect. And again, we can do it for x approaching negative infinity similarly. Pardon me. And the idea is that whatever that graph is doing on those far ends, our graph would be getting closer and closer to that 2/3, right? And so what happens elsewhere in the graph, and again, I'm just making that graph up, right? But what happens elsewhere in the graph, and again, there's probably going to be some horizontal or vertical asymptotes with that rational function, but neglecting that idea. This is kind of concept that, okay, we'll deal with what happens in the middle with our first derivative, second derivative discussion where we're increasing, decreasing, but then we can look at what happens at the ends. So that way we can see if I did get a critical number that looks like a maximum. If I know that everywhere else will kind of level off at 2/3, that might be the absolute max happening there, okay? And minimum, whatever it might be. All right. Okay. All right, so now we got to that work, but then what kind of comes up then is, well, what if, in this next example, right, what if I want to take this limit, I'll borrow this one from the book, okay, something interesting here. What do we got? Okay. What if I take this limit as x goes to infinity of this natural log of the square root of x over x squared? Okay. So again, taking another limit at infinity. But now in this case, now that we have that square root of x, we've dealt with problems with infinity and those radicals, right, before. playing around with how we can manipulate that notation and so on, right? But an added layer of difficulty is, well, okay, how can we divide by our kind of highest power with that root x trapped, locked inside the natural log, right? So adding that extra layer, that extra function, right? When it's polynomials, that's always nice and simple. That's why we deal with those first to get us used to these practices, these steps. And then, of course, we incorporate more dynamic, complex functions. But then we have to figure out, okay, well, how can I deal with those, right? And so that action that we would have managed in chapter 2, divided by the highest power, might not be as simple, as straightforward with these types of functions. Or later on, we might deal with something with a cosine, a trig function, right? So that's where we bring in our topic for today, okay? All right, so with that said, still thinking about what happens at these kind of interesting locations, positive, negative infinity, elsewhere as x approaches 0 in certain cases, right? If we get a 0 in denominator, something strange is happening there as well, right? So kind of thinking about those instances. So in that case, we can look at our other indeterminate forms. Okay. And a new method to evaluate the limit. Okay. So thinking about these problems where we have this limit as x approaches a, where a can be infinity, negative infinity, value 0, x approaches 1, x approaches negative 5, whatever it might be, right? And so when we look at these kind of limits involved, okay, and we get more than likely a rational type function, okay, going on. If this limit is going to go to 0 over 0, right? That's what we talked about before using algebra, right? This limit as x approaches a, more than likely these rational functions, right? Now we can also start to incorporate an infinity over infinity. So that's kind of like that last problem, or the first problem I should say, okay? Or even this problem here, that as I start to let, x go to positive infinity, all right, that those polynomials like a 4x cubed, 6x cubed, those are just going to continue to get bigger and bigger. So we get that infinity over infinity case, okay? And then if we get these forms of 0 over 0, infinity over infinity, before we would say to use our algebra to manipulate, okay? But sometimes the algebra is not going to be as helpful a tool. So now what we can do when we have indeterminate of these forms, now what we can do, we can use LHopitals rule. Okay. L'Hopital, I think that's how it's pronounced. All right. What it says is the following. Okay. L'Hopital's rule says all right, states if that limit as x approaches a of f of x over g of x, if that result looks like that 0 over 0 or infinity over infinity, then what happens that we can look at that limit and it's going to be equivalent to, it's going to be the same as taking the limit as x approaches a, where that be infinity, 0, whatever that number, that limit stays the same, but we can actually compare the ratio of those derivatives. So it's not a quotient rule. Just take your derivative of your numerator, derivative of your denominator separately, and compare that ratio. Okay? Because when we're comparing, we're doing this limit, we're trying to see how these two functions are interacting, right? And so we might not see an exact value that we can determine with those set y coordinates, right? So if we start to compare their rates of change, we're seeing, okay, well, how quickly is f of x changing? How quickly is it increasing or decreasing, right? How quickly is g of x increasing, decreasing? Look at those comparisons of rates of change, and we can make some decision, right? If they're change at the same rate, they're kind of growing or falling at the same rate, then they'll kind of balance each other out, and we'll figure out that result. If f of x is increasing much more rapidly than g of x, this has a bigger derivative, higher value, right? Then that value is going to kind of dominate. It's going to get bigger and bigger, and we might go to positive infinity. Or vice versa, if g of x is getting bigger much more rapidly than f of x, or maybe fx decreasing, g of x is increasing, right? Those kind of opposites. We'll see that maybe this will go to 0 or some other value. So we can look at the rates of change to see in the end what that limit will be equivalent to, okay? And again, I'm not going to do too much in development of that proof and whatnot, okay? You can look in the book. I think they have that discussion, right? I just want to use that consequence, that result, okay? So we can say that if I get one of these particular indeterminate forms, okay, 0 over 0, which we're used to seeing, infinity over infinity, we kind of talked about. Instead of having to go through some of those other algebra steps using the conjugate, factoring, canceling, which of course those should hopefully still work, most definitely. But if we get something that's a little more challenging, we can just hit it with the derivative now, right? So again, a little bit of luck of having that derivative on our side, which we didn't have back in chapter 2. It'll allow us to deal with these expressions, okay? So let's look at those two examples that one we've done and one we've talked about to manage, okay? So for example, going back to that very first problem, taking that limit as x goes to infinity of that rational function, 4x cubed, let me copy down my numbers just so it looks the same, minus 5x squared plus 8x minus 9 over 6x cubed plus 2x squared minus 4x plus 1. All right, so this first one is even going to be a little bit longer. Not longer, but interesting, I'll say. So when I look at this problem, right, just like we would do back in chapter 2 with our limits there, the first idea is kind of like a direct substitution. What's going to happen if I actually plug in, if I let this x go to infinity, right, what's going to happen if I let those x get bigger and bigger? This is going to be that case where we have infinity over infinity, right? So imagine plugging those in. When we have actual solid numbers, as x approaches 0 or -2, something like that, then of course that similar direct substitution shows up. And it hopefully makes sense there. Okay, so when I get that infinity over infinity, as long as it's one of those cases, infinity over infinity or 0 over 0, what we can do, we can use LHopitals rule, right? So I'm going to put this little equals LH, LHopitals. And so now what we're going to do, we're going to keep that limit as x goes to infinity. That limit doesn't change, but now we can differentiate. We can take that derivative, right? So if my numerator f is 4x cubed minus 5x squared plus 8x minus 9, denominator g is 6x cubed plus 2x squared minus 4x plus 1, I can take that derivative, so f prime 12x squared minus 10x plus 8, g prime 18x squared plus 4x minus 4. Make sure I get my signs right. Okay. So LHopitals rule says that I can't calculate here, so I can use those derivatives as their ratio instead. So I can drop in 12x squared minus 10x plus 8, numerator. Denominator, taking the derivative there directly, 18x cubed plus 4x minus 4. Again, not a quotient rule. We're just taking the numerator's derivative, denominator's derivative, putting those in place. And now we say, okay, can I evaluate here? But again, this one shows up again. Is I let x get bigger and bigger. Oh, sorry, I think I messed my x one up. This should be an x squared. There we go. Sorry about that. But this part, still infinity over infinity, right? As I plug in bigger and bigger values, the numerator is going to continue to grow. The denominator is going to continue to grow. Okay. So in this case, we can see, and it's possible, it's still that same indeterminate form. We're going to use LHopitals again. Right, and so we can keep on hitting it with this LHopitals rule, keep on using those derivatives as long as we have infinity over infinity or 0 over 0. Okay? And so going through it, LHopitals again, still taking that limit as x goes to infinity. Looking at this, now doing our power roll down, 24x minus 10, 16, oh, it's 36, sorry, by 2, 36x, right? 2 times 8, there's 16 plus that 1, okay, carrying that 1, we get that 36x better plus 4, boom. Looking at this again, is linear, a little bit better, but still, as I let x go to infinity, we're still getting that infinity over infinity, meaning we're going to use it LHopitals rule again. Right? And so we, as long as we have that infinity over infinity, 0 over 0, we can keep on hitting it with LHopitals rule. Is once that format changes, once I start to get like 0 over infinity, okay, then infinity over 0, that's going to be something strange happening. But that's when we go back to our previous discussions and think about what's happening there. But as long as 0 over 0 or infinity over infinity, LHopitals rule a valid operation. So LHopitals rule again, the limit as x goes to infinity. And now taking the derivatives one last time, 24 over 36, right? Those linear terms, we just get their coefficients finally. And now in this case, it's just a constant, right? The limit of a constant is just a constant. That same 24 over 36. I'm going to zoom out a little bit. And then reducing here, right? We can divide these both by what? 6 works. Anything bigger? 8. No, so let's try that part. My algebra is going on my head. Oh, 12 would have worked, huh? But that's all right. We could divide here, right? 4, 6, and divide by 2. And like I mentioned, if you could think about it, I could have divided by 12 earlier, but that's all right. And we get that same 2/3, okay? But this is a nice rule. Right? We just take our derivative, a numerator alone, take derivative of denominator alone, and just kind of keep working through those derivatives until we get to an expression that either, when we plug in our value directly, we get a nice real number result that we can compute, simplify, or just keep on hitting it. We get a constant at the end with these polynomials, right? It just keeps on knocking down the exponents. And then this, again, still going to be that horizontal asymptote for our graph later on, okay? All right. Not too bad. So let me get my paper, and let's look at that next example, okay? So that other problem I had brought up, I'll copy it down here. And just for guidance here, I did borrow it from the book. Boom, that last one. This one I made up, but let's look at this example from the book. I know I had written it out. There we go. This is problem number 22 on page 311. 311. Okay. Running too fast here. And we're taking this limit as x goes to infinity, the natural log of the square root of x over x squared. Okay. All right. So looking at this, and again, sometimes with these problems, like thinking about the graph can also help. All right. When it comes to exponentials, the natural log, some of these other functions, I think we had talked about the exponential and the arc tangent, the inverse tangent. I think we had talked about those fairly briefly, but I did bring them up. Okay. But what we can kind of see in this function, right? Thinking about these two functions, if this is my f, the natural log of x, that graph, the natural log in general is that arcing curve going upwards, right? By taking the square root, this might alter how rapidly it's increasing. But again, this function is increasing as x gets bigger, the y value does climb. It might be a really slow ascent, but it does grow. And then if our function g is that x squared, of course, that one probably a little bit less worrisome, right? Of course, this one, as x gets bigger, it's going to go to infinity, right? So looking at this information, we can start to plug in numbers if you want to. Let x equal 10, 100, 500, 1,000, whatever it is. And you'll see you get really large numbers over really large numbers, okay? So when I look at this limit as x goes to infinity of this expression, this is going to be kind of that infinity over infinity case. And we'll see other versions in just a minute. I'll back up and we can try another problem, okay? But looking at that, so if I have that infinity over infinity, we can use LHopitals rule and take this limit, right? That's going to be equivalent to taking this limit as s goes to infinity. And now we have to take the ratio of those derivatives, all right? So again, over here, if my function f, the numerator is the natural log of the square root of x, right? That's going to be the natural log of x to the 1/2 power. Let me know if that's too small to read. So when I take that derivative, f prime, the derivative of the natural log, right? That's 1 over whatever was inside that x to the 1/2, or that square root of x, I can put that right back. Then we have to multiply by the derivative of that inner function, derivative of what was going on inside the natural log, 1/2 x to the negative 1/2 power. Okay? So that f prime, 1 over root x times 1 over 2 root x, multiplying across 1 over 2x. Okay? So that's what's going on in that numerator. There's my derivative of that expression. We can double check, practicing our derivative skills there. The denominator, my function g, x squared, is derivative, a lot more straightforward, 2x. Nice simple power rule there. And now we're taking this limit of this complex expression, this complex rational expression. So taking that limit as x goes to infinity, right? Maybe a little redundant, but just to enforce, right? We're taking that 1/2 dividing by, or that 1 over 2x, sorry, dividing it by that 2x, right? That's what that expression looks like. So just doing our algebra here, we're going to get that case. And again, not to belabor it, but just so that we're taking our time at this stage, that division turns to multiplication. We take the reciprocal like so. And so this boils down to taking this limit as x goes to infinity of 1 over 4x squared. Pushing that up. Okay. And so now looking at this case, as I let x go to infinity, right? 1, that's going to be the same. But as I let x go to infinity, get bigger and bigger, that denominator, I'm going to say that goes to infinity, right? So this is similar. This is like what we saw in chapter 2, right? A constant 1 over this variable term. As that denominator gets bigger and bigger, right? That constant over infinity, that's just going to go to 0. So that limit as x goes to infinity for that natural log root x over x squared, that's going to go to 0. Meaning, as we graph that out, is going to settle to the x-axis, that y equals 0, as we graph it further on. So let me grab my graphing calculator quick just to illustrate. Graph that real quick. Natural log square root of x over x squared. Okay, so just very briefly, there's my equation. Let's graph it. I know I'll probably have to change my window, but that'll be all right. Okay, it's pretty small there. And even that's not that great. But, right, and again, maybe I can bring in my computer graphing tool, okay? But if we start to zoom in down here, right, we can see as that as the x goes on and on, right, the y value is flying slower and slower, right, dropping down, getting closer and closer. That's the x-axis, y equals 0, okay? All right, and depending on time, I might bring up like that Desmos graphing tool on the computer, the website, and we can graph it there to inspect, right? But going back to just our discussion, that when we looked at this limit, here in this format, I couldn't really tell what's going to happen. Even looking at my individual graphs, right, maybe I can see, well, it looks like x squared is growing pretty rapidly. Natural log grows at a pretty slow clip, pretty slow rate, okay? But maybe it'll balance out. We're not sure. So that's why we go through this work, right? And what it's identifying is that when we looked at their rates of change, that denominator is growing at a much faster rate than the numerator expression. So definitely it's going to dominate. It's going to get really big fast compared to the numerator. So that's why we're getting, okay, the denominator is going to blow up, go to infinity, and zero out that ratio, that rational expression in total. Okay. All right. And again, maybe that still takes some time to think about, but if it's clear, wonderful. If not, okay, it takes some time to develop. We can do the algebra part of it, the calculus part of it first, and then that more deeper kind of understanding of what we're comparing definitely takes some time to kind of sit and think about. Okay. And so then for that numerator, that derivative, right? So our original function, the natural log of the square root of x, or that square root of x is the x to the 1/2 power. Okay. And so then when I start to take my derivative, remember the derivative of the natural log is 1 over whatever was inside, 1 over that x to the 1/2, 1 over the square root of x. And then for the chain rule, the derivative here, 1/2 comes down, x to the negative 1/2, right? So that, right, taking 1/2 minus 1, negative 1/2 power there. And then now this part, the original natural log, 1 over what was inside. And then now the chain rule part, 2's in denominator, x to negative 1/2, breathe it down, and then combining there. Okay, good. Definitely, the natural log is always a little tricky. And watching out for that chain rule extra component of it. Wonderful. Okay, good. All right, so now let's do one more of these. Okay, at least, of course. And this time, let's have something go to a place other than infinity, right? Of course, infinity, that's going to be the one that we really start to think about using L'Hopital's, okay? But it's not always that case. So for this next example, let's jump up to here. Let's try number 18, see what that looks like. Same page, page 311, right? One problem or two problems up. And we're going to take this limit, this time as theta goes to pi, this angle. We're going to bring in our trig functions. Numerator, 1 plus the cosine of theta. Denominator, 1 minus the cosine of theta. Okay, and there's probably some other techniques we could use. Sorry, push that up. Some other techniques we could bring in and incorporate, right? Even all the work we had done back in chapter 2, we could talk about. And something that comes to mind off the bat for myself looking at this expression, right? When we have a 1 minus cosine in denominator, for myself, I start thinking about like Pythagorean identity, maybe multiplied by the conjugate, 1 plus cosine, and then maybe it'll look like something we can exchange, right? Do that in numerator as well. That might be an idea. That's just the algebra side of it, okay? But let's look at what happens if we plug in, okay? Or actually, this one might actually work out nicely. Let's check it out, okay? Thinking about this real quick. So I take that, and then we do our direct substitution, okay? That's going to be 1 plus the cosine of pi, 1 minus the cosine of pi, okay? There we go. Let's make sure I get this organized, pi. All right, and so look at this, cosine of pi, think back to our pre-calc, cosine of pi is -1. And so in this case, we're getting 0 over 2, right? So in this case, with our direct substitution, we're already getting a real number result. It's not undefined. That's what we're kind of hoping for. That's 0 over 0. Okay. Infinity over infinity. Right? Like I mentioned, I was already thinking about some algebra, but it wasn't necessary. Okay. But in this case, probably a good example. We'll do another one here. If I can do my direct substitution, just like we talked about before, and I get a number we can compute, right? That way, nothing special was needed. That's just equal to 0. Right? No special rules or work needed. We didn't get an indeterminate form. It wasn't 0 over 0. Infinity over infinity. So in this case, it's just a matter of plugging away and done. And we can go to look at the graph and see that that's definitely where we're going. It's defined there. No issues there. So that one, right? And again, that probably just kind of opens that discussion that a lot of times, right, we learn a new trick and we just want to use it right away, but it might not be necessary. Okay? All right, so now let's do this one. Number 16, right above it. There we go. Page 311. We're going to take this limit as x goes to 0 of x squared over 1 minus the cosine of x. There we go. And again, any questions on number 18, let me know. But again, that hopefully just kind of reminds us that before we just automatically try a new action, go through the basic steps first, and it might be pretty simple to evaluate, okay? All right, so now with this number 16 problem then, when we do our direct substitution here, plugging in that 0 for x, we're going to get 0 in the numerator, 1 minus the cosine of 0, 1. So there we go. There is our indeterminate form. This is a format, a result that we can apply L'Hopital's rule to enforce, right? But again, maybe other algebra skills we can try. But since we have a polynomial, an algebraic function, and this trig function, right, it's not going to be as easy to meld those together, okay? So rather than trying algebra, let's do L'Hopital's rule, okay? So here, applying L'Hopital's rule, LH above that equal sign, just to remind myself, okay, I'm now going to look at the derivative. Still approaching 0. Dealing with the derivatives, the numerator, right? If our function f in the numerator is x squared, f prime 2x. Denominator function g, 1 minus the cosine of x. So that means its derivative, derivative 1, that constant 0 goes away, right? Negative stays, but then the derivative of cosine is negative sine, just reinforcing why we get a positive sine of x in this denominator. Okay? The derivative of the cosine is negative sine, the negative, the minus is already hanging out, negative, negative, positive, okay? And then if I do my direct substitution here, plug it in 0, we still get a 0 over 0 case, right? So kind of thinking about that, I can evaluate. So again, L'Hopital shows up, taking a limit as x goes to 0. In the numerator, our derivative, 2x, right, or our function, 2x is derivative. If you want to change sign, then we call it capital F. Sorry for the bumping around, just so I don't confuse with this notation, right? So now my numerator function, I'll call cap F. 2x is derivative 2. The denominator function, I'll call capital G, sine of x, is derivative the cosine of x, right? So placing those, 2 over the cosine of x. And now direct substitution in this case will lead us to something interesting, or something with a numerical result that we can manage. 2 over the cosine of 0, right? Which is 2 over 1. So in the end, our limit 2. Zoom in out a little bit there. Okay. So again, we saw the first example, right, where we need to do L'Hopital's rule multiple times. As long as you're getting 0 over 0 or infinity over infinity, okay, we can use L'Hopital's rule, that nice result, taking the derivative of the numerator, derivative of the denominator separately, and compare the ratio, the fraction of those quantities, those expressions. Okay, and so sometimes in our problems, we didn't see one today, right? But sometimes in our work, as we start to go through, we'll initially have that 0 over 0 indeterminate form. But as we start to apply L'Hopital's rule, it'll kind of flip-flop sometimes. It'll go from 0 over 0 to infinity over infinity, right? When we deal with polynomials and whatnot, how we get those complex rational expressions, how terms move from numerator to denominator with negative exponents, so on, okay? You might start to see it where it switches from 0 over 0 to infinity over infinity, so on, but it's still the same kind of classification of that indeterminate form in which we can apply L'Hopital's rule, okay? All right, so we'll see some other versions of this, as well, not version, but other indeterminate forms. The most common discussion we have, and the one that we always kind of work on, is those ratios, 0 over 0, infinity over infinity. But another common one we might see, I think we might have talked about it before, is those cases of having like 0 times infinity, right? Because again, we're kind of built to, or kind of enculturated to think anything times 0 is going to be 0. But again, with these limits, we're approaching 0. So we're not actually taking 0, but a really small fraction, a small decimal. And if we're multiplying that by an infinity, some really large number, it's not necessarily going to 0 out. Maybe it's going to kind of cancel and simplify down to a set value, okay? Or maybe sometimes, again, think about that rate of change. If it's approaching 0 pretty quickly, it's going to really draw down. It's really going to pull down anything climbing, and it might go to 0. So we start to see other formats, other indeterminate forms, 0 times infinity, right? Sometimes powers, 0 to the 0 power, okay? So some of those kind of interesting. We'll talk about me really briefly probably on when we come back, but this is the ones we definitely see much more often, okay? All right, so I'll leave it at that. We'll have our quiz this week covering that section 4.3 stuff, okay? So intervals of increase and decrease, intervals of concavity, those inflection points, that's what we're gonna be working on for our quiz this week, okay? Right on. And so I did post your scores for the exam too. I just have to take the time to take pictures, scan, and send that feedback back to you. But you should be able to look on your quizzes page, I think, or assignments. And for the exam too, I did post your scores, okay? So if you have any questions, definitely let me know. I'll be working on taking pictures, getting those scanned so I can get those emailed to you. So bear with me for another couple of days with that, all right? And then we'll have an exam. Depending, we'll probably have more quizzes, but since we are kind of getting close to that final, I'm debating whether we're going to have an exam 3 or not, okay? But as we get close, because this chapter 4 stuff is 4.5 and then optimization, so I'm not sure. Depends how close we get to that final exam date. So probably next week I can get a better gauge and we can inform about that next exam possibility, or if we're just going to run right into the final and just take a bunch of quizzes, okay? Right on. Very good. Thanks for that question. All right. So that's it for me. If you have any questions, stick around. Otherwise, have a good rest of the day. Take care. Be safe out there.